Imagine a world where flat tires are a thing of the past. No more punctures, no more pressure checks, just smooth, reliable rides. Welcome to the world of airless tires. So, what are airless tires? Unlike traditional tires that rely on air pressure, airless tires, also called non-pneumatic tires, use a solid or structured design to support the vehicle. That means no air, no leaks, and no blowouts. Let's get into the engineering behind it. At the heart of an airless tire is a flexible internal structure, often made of high-strength polymers or composites. Most airless tires use a spoke-like internal structure, for example Michelin's Tweel, or a honeycomb lattice to support the load and absorb shocks. These structures deform under pressure and return to shape, mimicking pneumatic cushioning. The outer layer is a rubber tread, similar to traditional tires, designed for traction, wear resistance, and grip. Some designs include a shear beam between the tread and the spokes to distribute loads evenly and improve ride comfort. The spokes and tread are typically made from high-performance polymers, urethane or rubber composites. These materials are chosen for flexibility, durability, and resistance to fatigue. The tread may include carbon black or silica for enhanced wear resistance and grip. Here's what really makes airless tires special. First one is load-bearing capacity. In airless tires, the load is carried entirely by the structural elements, spokes, web structures, or honeycomb designs rather than air pressure. These designs are engineered to handle specific loads based on vehicle types. A passenger EV might require a flexible, lightweight design for comfort and efficiency, while a military vehicle would need reinforced structures to handle high payloads and harsh terrains. The design challenge is to distribute the load evenly while maintaining stability, ride comfort, and durability without the cushioning effect of compressed air. Secondly, comes rolling resistance, a critical factor that affects fuel efficiency and battery range, whether it's in a diesel-powered heavy machine or an electric vehicle. Rolling resistance is the energy a tire consumes while it deforms as it rolls under load. In traditional pneumatic tires, some energy is lost due to repeated flexing of the sidewalls and tread. In early airless tire designs, rolling resistance was often higher because the rigid structures didn't flex optimally, leading to more energy loss. But here's where engineering steps in. Modern airless tires use specially tuned spoke geometries and advanced polymer materials to minimize unnecessary deformation while maintaining flexibility where needed. The spoke patterns are designed to flex just enough to absorb shocks without causing excessive drag, and the materials are carefully chosen to reduce hysteresis losses, which is the energy lost as heat when the structure flexes and returns. What's the benefit? Some of the latest airless tires now match or even outperform pneumatic tires in rolling resistance, which translates to lower fuel consumption for diesel machines and more kilometers per charge in electric vehicles. And the best part? They maintain this efficiency without ever going flat, providing consistent rolling resistance throughout their life, which pneumatic tires can't guarantee as they lose air over time. Third comes heat dissipation, a factor often overlooked but critical in tire design. When tires roll under load, they flex repeatedly, and this constant deformation generates heat inside the material. In pneumatic tires, the air inside helps in absorbing some of this heat, and the structure is designed to radiate heat to the surrounding air. But airless tires face a unique challenge. Since there is no air inside to help with cooling, heat management relies entirely on material properties and structural design. To tackle this, engineers use ventilation channels, open spoke structures, and specialized materials with high thermal stability. These channels and gaps allow air to flow through the tire structure as it rotates, carrying heat away and keeping the material at safe operating temperatures. Moreover, the materials used in airless tires are chosen not just for strength and flexibility, but also for their ability to handle thermal expansion and resist heat-related degradation. Why is this important? Excessive heat can lead to material fatigue, reduced structural integrity, and faster wear. By managing heat efficiently, airless tires maintain consistent performance even during prolonged operation at high speeds or under heavy loads, whether it's on an EV cruising on the highway or a military vehicle operating in a desert environment. In essence, effective heat dissipation in airless tires is what makes them practical for real-world use, allowing them to match the durability and performance standards of pneumatic tires while providing the added benefit of never going flat. Fourth comes noise and vibration management, a crucial factor for comfort, safety, and operator fatigue, whether it's in an electric car or a heavy machine. Traditional pneumatic tires naturally dampen road vibrations and noise due to the cushioning effect of compressed air inside. However, early airless tire designs faced criticism for being noisier and transmitting more vibrations to the vehicle because there was no air to absorb the shocks. So, how do modern airless tires solve this problem? Engineers use advanced spoke geometry, variable thickness structures, and specialized damping materials within the tire's architecture. The spokes are designed to flex in a controlled manner, acting like mini shock absorbers that dissipate vibration energy before it reaches the vehicle. Additionally, tuning the spoke angles and patterns helps in reducing the resonant frequencies that cause noise when the tire interacts with different road surfaces. Some designs incorporate layered materials with vibration damping properties to reduce the transmission of harshness to the cabin. A result? Modern airless tires have significantly reduced road noise and vibrations, achieving comfort levels close to or even matching those of pneumatic tires. This advancement is particularly valuable in electric vehicles, where tire noise is more noticeable without engine sounds, and in heavy machinery, where reducing vibrations helps prevent operator fatigue and increases equipment lifespan. So, while airless tires started off noisier, today's designs have turned this weakness into a strength, providing a smoother, quieter ride while maintaining their core advantage: flat-proof reliability. They're puncture-proof, low-maintenance, have a longer lifespan, come in eco-friendly options, and are perfect for off-road and industrial use. Big names like Michelin, Bridgestone, and Goodyear are leading the charge. Now, it's not all smooth sailing. There are still challenges like perfecting ride comfort, managing heat, and bringing costs down. But with ongoing research and development, airless tires are inching closer to hitting the mainstream. Flat tires may soon be history. If you found this cool, hit that like button, subscribe, and let me know in the comments. Would you trust airless